OCR A A-level physics. This is my fourth video for Gravity and Astrophysics, and this is about spectra. Maybe stuff that you should have done in waves in the lower six, but it's actually in this bit of the specification, so I'm going to go over it again. So now this is a hydrogen discharge lamp. It's a lamp which has got hydrogen atoms at low pressure. And we excite these atoms by banging them with electrons. So we accelerate electrons and they bang into the hydrogen atoms and we get light. But we don't get Roy G. Biv, we get light with very definite wavelengths. And that's called the hydrogen emission spectrum. And if you look, we can actually measure the wavelengths, and I'll tell you how we do that in a bit. You see a very prominent red line, that's called hydrogen alpha. So we get light of very, very definite wavelengths that we can measure. And other elements have their own characteristic emission spectra. In other words, different elements give you different colored lines. And if you measure the wavelength of these lines, you can find out what that element is. It's like a barcode. Like if you read the barcode, well, that's baked beans or whatever. So these spectra are like barcodes that we can use to identify elements. Okay, now that was an emission spectrum. This is an absorption spectrum. And again, what happens is that the atoms of hydrogen or any other element absorb the same wavelengths. Okay, this is actually the absorption spectrum for our sun. And by looking at it, looking at the black lines, we can tell what the sun is made out of. Okay, and the darker the line, the more of that element there is. So we see very dark lines at 656 nanometers and 486 nanometers, etc. And that tells me that the sun contains a lot of hydrogen. Yes, because those lines are in the hydrogen spectrum. And it's the outer layer of the sun which is absorbing exactly the same wavelengths. So we have an emission spectrum and we have an absorption spectrum. And the more abundant the element is, the darker the lines are. If you look at the spectrum of light from a star, these black lines coming down, yes, they're the black lines on the diagram above. Okay, so this black line here is your hydrogen alpha, yeah, your 656 nanometers. Yeah, the outer layer of the sun, it's actually called the chromosphere. Below that, you've got the photosphere that produces lots of light, and then the chromosphere absorbs certain wavelengths, okay? And hydrogen and other elements in the chromosphere absorb certain wavelengths, producing the absorption spectrum. Now, why do elements emit light with certain wavelengths, and how can we measure these wavelengths? Okay, so why do they emit light with certain wavelengths? Now, this atom is having a snooze. Okay, this atom has no extra energy. It's in its minimum energy state. It's called its ground state. It can't have any less energy. So we excite it. There's various ways that you can excite an atom. One way you can excite it is by banging it with an electron, or if they bang together hard enough, that excites them, or if they absorb photons, that excites them. So there's different ways to excite an atom, but the atom gains a certain amount of energy. Not enough energy to ionize it, but the atom becomes excited. You can imagine it going, ooh, it's all excited, and it doesn't like being excited. So at some point in the future, it will lose that extra energy by giving off a photon. And hopefully you remember this equation, E equals hf. So E is the energy of the photon, h is Planck's constant, f is the frequency. So you've got your ground state, you've got excitation, and then you've got emission. Okay, so what's happening inside the atom? Well, we explain this by drawing energy level diagrams. This is a very, very simple diagram. It's just a way of understanding what's going on, by the way. So the ground state we say is n equals 1, and then a higher energy level would be n equals 2. You can think about this, do you remember in chemistry, electrons and 288 and all that stuff, shells? You can think of this as being the same thing. So excitation, imagine an electron jumping up from n equals 1 to n equals 2, which is a higher energy level. And then at some point it falls back down again to n equals 1 and it emits a photon. So excitation, an electron absorbs a certain amount of energy, rises to a higher energy level. Emission, the electron falls to a lower energy level and a photon is emitted. And the energy of the photon is equal to the difference between the two energy levels. This is a more complicated diagram. This shows energy levels for a hydrogen atom. We will only ever do a hydrogen atom. Other atoms, they've got more than one electron. It's a lot more complicated. But hydrogen, very simple, just one electron. So n equals 1 is the ground state, and then it can jump up to other higher energy levels or fall back down again. If an electron gets to n equals infinity, then it escapes. Yeah, it has enough energy to actually escape. So the ionization energy of hydrogen is 13.6 electron volts. If you look at the diagram, yeah, this energy level here is minus 13.6 electron volts. So if we gave the electron 13.6 electron volts, then it gets all the way up to n equals infinity and the electron can escape. Notice that the energy values are negative. We are talking a potential well. Yeah, the electron is trapped. It can't escape unless we give it energy. So the electron is in a potential well, and that is why these energy levels are negative. Here's a question for you to do. Don't be lazy. Pen, paper, calculator. Get it done. And the answer is, so an electron falls from level 4 to level 2. Yes, calculate the energy of the photon emitted in electron volts and joules. Calculate its wavelength. What color will it be? So, right, so the difference in energies is 2.55 electron volts. So that will be the energy of the photon. That's 4.08 times 10 to the minus 19 joules. If we do E equals hf, and F is C over lambda, we get 488 nanometers. And if we look here, 488 nanometers, I reckon that's green. Okay, so the photon will be green. One note, by the way, anything that falls to n equals 1, those photons have lots of energy, and they're actually ultraviolet. So your visible photons are all the ones that fall to n equals 2. Okay, they're visible. Anything that falls to n equals 1, lots of energy, they're ultraviolet. The little falls around the top here, they're actually infrared. Okay, so any falls, I've done 2 of them, any jumps around here involve infrared. They don't have a lot of energy. Okay, they have big wavelengths, low frequencies. So how do we measure these wavelengths? We use a diffraction grating. So from basics, what is diffraction? So a wave goes through a slit, and if the width of the slit is about the same as the wavelength, then we get this diffraction, and the slit acts as a point source. Okay, so you've got your waves coming along. Yes, the waves come along and they go through a slit. There's a slit, and the slit acts as a point source, and that is diffraction. If we have 2 slits, then we get an interference pattern. And you remember Young's double slits, okay? If you don't remember it, revise it. Young's double slits, and you get constructive and destructive interference because the two slits are coherent. Yes, and we get maxima and minima, fringes we get, don't we? Constructive, destructive interference, etc. Revise it. What's going to happen if we have lots and lots and lots of slits? Well, it's just crazy. All these waves all over the place. Are they all going to cancel each other out? And now what happens is that they do all cancel each other out, except for in certain directions. So in the straight through direction, yeah, we get a maximum because they all add together because they're all in phase. And then there are other directions as well. In this direction here, hopefully you might be able to see on my diagram when the path difference between adjacent slits is a multiple of lambda. So the path difference between adjacent means next to each other is a wavelength, which is these red circles. We get a maximum. And we'll get a maximum there. And we'll maybe get a maximum here when the path difference is 2 wavelengths. And then we'll get a maximum here. So we will get very distinct maxima because there's lots of slits contributing, but only in certain directions at very definite angles. A diffraction grating is lots and lots and lots of slits. This diffraction grating has actually got 600 slits in every millimeter. That's a lot of slits. So 2 slits, how far apart are they? Well, if it's 600 slits per millimeter, then it's 600,000 in a meter. So 1 over that, they are 1.67 times 10 to the minus 6 meters apart. That is the slit separation. Okay. And if we shine a laser, which is monochromatic, through a diffraction grating, we see on a screen, we see these dots. And these dots are called maxima. You've got your 0 order maxima, which is straight through, and then first order either side, and then second order either side. And these are maxima, and it's where the waves from all of the slits are interfering constructively. Okay, as we talked about on the last slide. N lambda equals d sine theta. That's for a diffraction grating. N is the order. Remember, it's like first order, second order, third order. D is the slit separation. You might have to work that out. You might be told it's like 80 lines per millimeter. So the slit separation would be 1 over 80,000. And then theta is the angle for that order. Here's a question for you to do. Red light of wavelength, doodah, passes through a diffraction grating, doodah. At what angle will the first order maximum occur? And there you go. So rearranging the equation, theta is sine to the minus 1, n lambda over d. N is 1 because it's first order. Lambda we're given. D, again, it's 1 over 600,000. And you should have got 23 degrees. So by measuring the angles that maxima occur, you can work out the wavelength of the light. If you put white light through a diffraction grating, you would get continuous spectra for each of the orders. So if you look at this diagram below, you'd get Roy G. Biv, and the bigger wavelengths would happen at bigger angles. Notice, look, that red is further away on each one, further from the middle. But we were talking about spectra, so this is how we actually measure the wavelength for the different lines, and then we can identify the elements. Yes. Astronomers use things called spectroscopes, which contain a diffraction grating, and that's on the end of their telescope. And so they point their telescope at the star, and they can then measure the spectrum of the star. Okay, you get this continuous spectrum, which is like the hump thing, but then you get the dark lines that we were talking about before, and by measuring the wavelength of these lines, you can work out the composition of the star. And as we'll see in the next video, you can actually learn an awful lot more about the star by looking at this spectrum.